Okay, so hello everyone, I am Harshal Jain, and in this video we'll be learning about AVL trees, binary heap, and red black tree. Okay, so these are three different kind of trees which are actually under binary trees, like binary search trees, but we use them for more efficiency. Okay, so we use AVL trees with some rotation, we use red black tree with rotation as well as coloring, and we use binary heap tree to store in max heap or min heap format. So we'll see them one by one, and this I can say that when I learned this topic first, it's pretty much confusing. Okay, like you need to know when you are about to rotate things and when are you about to recolor in different scenarios, which we'll be looking into today, and we'll be taking some examples. I will explain you by drawing figures so that you get a better idea, not just theoretical definition. So we'll see that today. Okay, so what we'll be covering? We'll be covering AVL trees, then we'll be covering red black tree, then we'll be covering binary heap tree. Okay, so these three trees are important. Then after knowing the practical part, we'll be applying the code, okay, in JavaScript. So let's continue. So before moving on, in the live chat you can see that we have a link for a course provided by Geeks4Geeks, that's DSA in JavaScript. Okay, so if you want to purchase that course, you can click on that link, and you can also check out description for the same link. You'll find this course link, and this is for people who are beginner in DSA, like who even don't know basics of DSA. Can start with this, because since JavaScript is a easy language, and if you want an easy language, or if you want to learn DSA in some web development technology, like JavaScript is used in web development, so you can learn it in JavaScript definitely. And you can see that we have topics here, so if you want to explore, you can. All the topics are mentioned here, and you can learn things in this way. Okay, so everything is present here, including data structure and algorithm. And as you can see, we have also covered the basics also, so you can check out this course. All right, so this is a paid course, so for viewing this course you need to purchase it. All right, so now let's go to whiteboard, and I will show you how AVL tree works first. Okay, so before that, you need to know the basics of binary search trees. So if you haven't watched my previous videos, please watch them, because the code is pretty much same and the logic is pretty much same. Like the order which we will be writing the nodes will be same, but yeah, there will be some rules. Okay, so please watch the previous videos. If you don't find my previous video, you can simply visit Geeks4Geeks practice channel, that means the channel which you are looking at, and in the live chat you'll find, sorry, in the playlist section you'll find that we have view full playlist. Okay, so this is the playlist, data structures using JavaScript. You can check out this playlist. Inside this you'll find all of my videos which I have covered, and especially watch the tree videos because they are very important. All right, so now we can continue, and here what I'll do is I'll just simply first create a whiteboard. All right, so let's just keep it plain today because we need coloring and I don't want any interference of color, background color. Okay, so what I'll do is, first of all, I'll tell you the logics of rotation, because first of all we'll be starting with AVL tree. Okay, so AVL tree basically is a different kind of tree in which we write things in order, where we avoid some kind of left side. You can say that if tree grows only left side, okay, if binary search tree grows only on left side, that might be problematic. If binary tree grows on only on right side, that might be problematic. What can be the cases? Let's see that. Okay, so suppose you have a case where elements are actually assigned one by one, right? In any tree, elements are assigned one by one, that is 10, 20, 30, 40, 50. You have some kind of tree like this, so obviously the tree will be rightwards slanted. So this is actually, you can also call it right skewed, by the way. So this is actually problematic because the search timing, or if you want to insert anything, things will be taking more time. Okay, the time complexity will increase as the height of the tree is increased. Okay, so we need to remove that. That is the problem with binary search trees. So I'll just give you an example so that you get a better understanding why we use AVL trees. All right. So let's take an example. Guys, just a minute. Okay, so we'll take an example, a very basic example, which will help you understand why do we need AVL trees. If you already know binary search tree, you must be thinking, why do we need AVL trees or any other kind of tree? Basically, the insertion method is different in these trees. So what I'll do is I'll just take an example of some digits. So it's actually helpful. This tree is very helpful when you are talking about searching and insertion in any tree, because it decreases the height of tree as much as possible. Okay, so let's take a BST. Okay, here what I'll do is I'll draw a diagram. Let's take a red pen, and first of all I'll just give it some numbers. Okay, so 10, 20, 30. Okay, just a minute. Yeah, so 10, 20, 30, 40, and let's give another one, that is 50. So as you can see that if I talk about binary tree, okay, binary search tree, what must happen? First element will be 10. Okay, because this is the root element. First element is the root element, we assume it in the binary search tree. It's not in the case of other trees, but in binary search tree we assume that the first element is the root element. So since it's the root element, the greater one will be on right side, so 20 will be here. Okay, again 30 will be here, again 40 will be here, again 50 will be here. Suppose if I want to search for 50 in the tree, okay, so in the worst case 50 is in the last. So this is problematic, as the height of the tree is very much. Okay, we need to decrease the height, and that's the problem with BST. Okay, this is a binary search tree, and that's the problem with BST. So this is actually a binary search tree. And if I talk about AVL tree, if you wanted to draw the same tree in AVL tree, I'll just give you a final outcome first so that you get an idea of what's actually what do you get in AVL tree. So suppose if you wanted the same tree in AVL, what would have happened? So in AVL tree we'll explain the steps later on, but right now you can see that the final result for the same tree would be like 30, 20, and obviously we'll be having some rules for these. And here we had 20. Suppose okay, let's skip another one. We don't have any other element, so here we don't have any other element, right? What I'll do is I'll just add another element named as 25, because I took an example that way. So if suppose you have 25, what you'll have is 25. 25 will be actually here. Okay, 25 will be actually here, because since it's lesser than 30. Okay, fine. So since still it's a bigger tree, so what I'll do is, if I want a smaller tree, what I'll do is in AVL we draw it simply like this. Okay, and here what do you have? 40 and 50, and you can see that the height of this tree significantly decreased. These are very less number of items, but if you have a lot of nodes, then definitely this will be very helpful as compared to a normal BST. Okay, so now we'll be looking how we can build this kind of tree. Okay, this kind of tree, how can we build this kind of tree? Okay, so let's begin. So what I'll do is I'll just start from here. Okay, so this video might get very long, so please wait patiently. Okay, if you have any doubts, please ask me on the live chat. I'll reply as soon as possible. So what is AVL? Okay, what is AVL? So let's understand what is AVL first. So AVL is simply a self-balancing tree. Okay, you can see that the BST was not self-balancing. Okay, it was actually, you can see in this case the tree was right skewed. Okay, it was towards the right, moving towards the right mostly. Okay, so it's right skewed. Similarly, we have left skewed trees. So this is a problem in trees, binary search trees. So AVL actually is known as a self-balancing tree. That means it's equivalent. It's equivalent. Okay, so difference of height between left and right side is not that much. That means not more than one node. Okay, so suppose the height is on the left side, it's 4, so it can be maximum 5 on the right side. Okay, I hope you are getting it. If the height of left side is 4, maximum can be 5. Okay, so I'll give you an example. If you want to find the height of left and right side, okay, this is a very important step which we'll use every time. So suppose this is the root node, and suppose we don't have any element here on the left side, but we have one element on the right side. Okay, so the height of left side is 0. Okay, and the height of right side is what 1, because we have one element on the right side, so it's actually -1. Okay, so since it's not 2, okay, or -2, we are fine. Okay, that means the height difference must be between either -1, 0 or 1. That's it. That's what you want to know. This is the rule. This is the rule. The height of left side as compared to right side must be either -1, difference is either -1, 0 or 1. So let's take another example. If suppose I didn't had any element on again on the left side, but I had one element on another element on the right side. So you can see that its height, I'll just take a red pen, its height was what? 0 minus 2, because 2 are on right side, and this is now -2. So this is an unbalanced tree. Okay, now it's an unbalanced tree. That means this node is unbalanced, not the whole tree. This node is unbalanced. So we'll perform some operation on this specific node, not the whole tree, on this specific node. And similarly, you need to calculate for each node. So suppose you have this, and in this case we didn't had any right child, so it's actually -1, so it's fine, and 0 minus 0, it's again fine. Okay, so you can see we need to perform operation only this node. Okay, similarly, if I take another example, let's take another example. Suppose we have another tree which has left child and right child. Okay, so what the height of this node? This node has an height of 0, because okay, let's make it red. This node has a height of 0, as left side is 1, right side is 1 node, so it's 0. Suppose we have another element on the suppose left side, on the left side, what will be the height? Now the height will be actually 1 minus, sorry, on the left side we have two elements. On the left side we have two elements, -1, that is 1. In this case it's 1. Okay, so left minus right will be the whatever will be the height. So you can see this height is still in our range, -1, 0 and 1. Okay, so it's still a valid tree. Okay, this is not an unbalanced tree. So again we draw another item here. Suppose we have some branch here. Suppose we have some branch here. Okay, and suppose we have one more element here. Okay, so now what's the height of this tree on the left side? Okay, so first of all you need to compare for each side. Okay, you need to compare for the each side. For its height is 0, right? Its height is 0, and its height is what? 1 minus 2, that is its height is 1. Now the height of top one is actually, you have to calculate from the maximum side, that is this is the first element, second element, third element. So the height of this left side is actually 3. Okay, you need to find the maximum height from the left side. This is the maximum height. Okay, this is the maximum height, so you will be calculating this one. Okay, this is the maximum height for this one, so 3 and again -1, so this is 2. Now again this is an unbalanced tree. Okay, so that's how you actually judge what node is balanced or unbalanced. So whatever node is unbalanced, you need to perform an operation on that node first. Okay, you might have some unbalanced node above this also, but you need to look for the first node which you get whenever you are trying this operation. Okay, so there are a lot of examples, we'll see that later on, but right now one more important concept in this is actually rotation. Okay, so we'll be performing rotation in any tree, and we'll know how actually rotations are performed in any tree. Okay, so for that we can do one thing. We can simply take a few examples. Okay, there are actually four types of rotations which we will see today. Okay, and these kind of rotations are actually used in AVL tree as well as red black tree. Okay, so in both of the trees, we'll just say that suppose we have a line here. Yeah, fine. Okay, so now what I'll do is I'll say that there are actually three types. First one is known as right. Okay, right rotation. This is the case for right rotation. Suppose we have a scenario where we have right skewed tree. This is simply for right skewed tree. Okay, so first element and suppose second element. This must not always the root, can be any element, because from any node you have a unbalanced tree. Okay, unbalanced tree. So this can be any node. Okay, so suppose this node is A, and again we have this node, and again we have this node. Okay, so we have three nodes here. So first, and yeah, so you can see that this will be the case for right. That means this is on the right side, this is on the right side, so you can see right skewed. Okay, again we have left. Okay, so left. So left simply means first element, second element, and this is the third one. Okay, so you can see that this is left side. Okay, left side, that means we have first, and then we have second, and we have third. So you can see that we have three elements here, and they are on left side. So you can see it's actually moving towards the left side. Okay, so here you can see that in this case we are on the left side. Okay, everything is on the left side. Now we have another case named as RL. Okay, RL simply means that the first, okay, sorry, that first is actually on the right side. Okay, first is also on the right side, that means first node is on the right side, then the second node is actually on the left side. Okay, so you can see that this is known as RL case. Okay, so we are not knowing right now what to do with these cases, we are just thinking that what might be the cases for doing operations. Okay, so this is the third case. Similarly, we have a fourth case for rotation named as LR. Okay, this is the fourth case, very important. And again, same things is actually happening here. We have the first, and then left side, and then the right side. Okay, so this is the case for LR. That means first we move left and then right. So again, A, B, C. So these will be the four cases which are very important and will always happen during any rotation. Okay, so we'll be looking into, of course, each node can have different childs also, but right now we are just assuming that they don't have any other child. Okay, so that it's easier. So here I'll just add a few lines. Okay, fine. Yes, fine. Okay, so these will be the four cases. So in first case, what must happen is, if you want to perform in this rotation in this, what must happen is simply you will be rotating from the middle element, that is from the B. So what will happen is, now B will become parent, okay, this is B will become parent, A will become its left child, and C will become its right child. Okay, C will become its right child. So this is the RR rotation. Okay, this is the RR rotation. And now we have another case which is left. That simply means that A will be the right child and C will be the left child. So it's actually rotating in this order. Okay, you can see this is the clockwise, sorry, uh, I got confused with that. So don't assume it as clockwise or anti-clockwise, because that might be problematic. What you can do is simply just assume that you need to break down. If you have things like that, you need to make it this. Okay, if you have things like that, you have to make it this. That's it. Okay, don't assume it as clockwise or anti-clockwise, else you'll get confused. Okay, so here I'll simply say that again we have it here. So what I'll do is, now A will become right child. Okay, A will become right child. So this is the case for B, A, and C. Okay, so you can see that this is actually LL rotation, and this is known as RR rotation, and then we have RL rotation. Okay, so what must happen in RL? RL simply means first you need to convert it into RR. Okay, whatever is the first letter, we need to convert it into that. So RR simply means that the middle switch the middle with the bottom one. Okay, that means if you take it as R, L, okay, R and L, you can see that the middle one is actually B and the bottom one is C. Okay, don't worry about their childs. Okay, C must be having some childs, B must be having some other child. Don't worry about their child. We are only talking about these cases. Okay, so first we need to convert this RL to actually RR. So what we'll do is, again what I'll do is, I'll just make it red now. So what I'll do, I'll simply say that the top will be the same, again A, but now what will happen is now the middle one becomes C, okay, and the right one now again becomes B. Okay, so now you can see we have actually switched both of them, and C is now actually on the right, that means in on the middle, and we have actually made it right skewed. Okay, so we have actually made it right skewed now. So you can see now this is right skewed. Then you need to rotate. Okay, now we have performed RR on it. Okay, we have performed, sorry, we have performed RL on it. We have performed RL on it. Then at the end you need to perform RR on it. Okay, that means first of all we converted it into RR, then whatever is the operation of RR must be performed. Okay, so this will be performed then. Okay, this will be performed that. Okay, so it will actually simply become C. Okay, what I'll do is I'll just write it here. So it will actually become C, and then A will be here and B will be here. Okay, so I hope you got this. This will be actually for this case. Okay, for this case we'll be having this. Okay, similarly suppose we have this LR. LR simply means that first what you'll do is we will perform rotation between these two. We'll convert it into LL. Okay, so first is A, then the second will become C in this case. Okay, C in this case. Okay, then we have B here. Okay, so we have B here. So you can see now it's LL. Okay, now what's for LL? Simply this operation. Okay, simply perform this operation. Okay, I hope this is visible. I think this is visible enough. Yeah, it's visible enough. So you will be simply performing the LL operation in it. Now, that means it will simply become, this will simply become, if I perform any LL operation on it, that means right now it's LL. From LR we have converted into LL. Now what's happening to LL? It's simply the middle one will be now the parent. Okay, now B will be here. Okay, so C, B, and this will be actually A. That's it. That's how you perform rotations here. Okay, so you please you need to watch this again if you don't get this. And actually I have a better presentation here, so if you don't get the rotations, what you can simply say is you need to visit GeeksforGeeks website and you will find this great article. Okay, AVL tree data structure, you can search for it and you'll find this great article. You'll see a better representation obviously, so with diagrams. So you can see that they have performed left operation here, left rotation here, it's actually converting it into this. Okay, similarly they have performed right rotation, similarly they have performed left LR rotation. You can see first they have actually converted it into LL. LR is actually converted into LL. That means the CAB is actually converted into CBA. Okay, then the CBA is actually converted into whatever is the output of LL. Okay, that means this. Okay, similarly RL is performed here. In RL, first of all, this RL ACB is converted into RR, that is ABC. Then this ABC RR is converted into final output, whatever is for RR. Okay, so you can say that this is very important. Okay, this is very important, and additional operation is performed in LR and RL. Okay, so please understand this very well, because this the initial thing which you will need. Okay, so we have understood the basic of requirement of AVL tree. Then you can actually see what are the applications it is used for. Index use records in database, where you don't have to search for long heights. Okay, it actually decreases the height, I told you. So you can see the advantages and disadvantages. All right, so what I'll do is I'll just close it now. Okay, fine. So let's continue. So this was very basic rotation which we have performed. Now we'll be using this rotation to create our tree, to work on our tree. Okay, so simply now we'll be taking one example. Okay, same example which we have used before. What example? The example which we took above. Okay, this example. Okay, we created this in BST and I told you what it must look like in AVL. So you can see that the height is obviously decreased. So what is the example? 10, 20, 30, 40, 50. 25. Okay, so we'll be working on this example and we'll be creating an AVL tree out of this example. I'll be showing you how we can perform insertion in this, because insertion is very important in this case. Okay, you can learn other operations later on, but insertion is the most important operation, and we'll be covering only insertion part. Okay, today's video. Okay, so what I'll do is I'll just add some space here. Then what's my question? My question is actually we have elements 10, 20, 30, 40, 50, and then at the end we had 25. So we need to perform AVL tree. We will need to create an AVL tree out of this. We are not creating a normal binary search tree. We are creating an AVL tree. Okay, every AVL tree is a binary search tree, but not every binary search tree is an AVL tree. Okay, this is the difference. So what I'll do is, first of all, you will be inserting the first element. Again, initially in AVL tree also, you will be assuming that this is the root element. Okay, that means you will be starting from again. Right now I'm not drawing circles. What I'll do is, okay, let's draw circles. It's easier. Okay, so what I'll do is, I'll just say that first element is 10. Okay, first element is 10, and then you are inserting, suppose you insert 20. 20 is greater than 10, so you'll be inserting it again on the right side. Okay, it's same. All operations of BST are also valid. All rules of BST are also applied on this. Okay, BST rules must be followed in AVL also. Okay, there are some additional rules, that is for rotation and so on. So here you can see, you need to first check when you are performing rotation. You need to first check that is this tree unbalanced. If it's unbalanced, then only you need to balance that tree. Okay, so that's what the AVL does. So here what we'll do is we'll simply find its height. So its height is actually on left side it's 0, and on right side it's actually 1, so it's -1. And our range must be what? Self balancing trees range is actually -1, 0 and 1, so it's in our range, right? -1 height is actually in our range. Okay, so now what I'll do is, okay, let's make it better. It's actually looking like, yeah, fine. So here now we add another element. Okay, now we add another element. So now the second element is, suppose first was first element which we inserted was 20. Okay, we inserted was 20. Let's say that initially we had 10, then we insert 20, then we have inserted the next element will be what? 30. So obviously 30 is greater, so we will insert it here. We will insert it here. First you need to perform insertion, then you'll see that what's the problem with this. The problem with this is now it's an unbalanced tree. Why it's an unbalanced tree? Because here you'll see that the height is actually, this is actually 0, left side is 0 and right side is 1. This is fine, this node is fine. Okay, this is -1, but in the above one now it became 0 minus 2 nodes, that is -2. The height is -2, which is out of our range, out of our range. So what simply mean, it simply means that we need to perform rotation here. Okay, how can you perform rotation here? Very easy. You just need to say that this is the case for what? This is the case for, actually it's the case for R. Okay, sorry, this is actually the case for R, right? This is the case for R. So what you'll do is you'll perform right rotation. Okay, so you'll perform right rotation. So here rotation will be performed 20, and this will be on right left side, 10 will be on left side, and then 30 will be on right side. Okay, so you can see it's like that. Okay, now it's fine, this tree is totally fine, so that's why I made it with green. Now we will perform another insertion. Another insertion is for, actually I'll write it here. Okay, so now we'll perform another insertion. I'll simply say the next element is actually 20. Okay, again root is now 20. Okay, so now you can see root has changed. Root has changed. Initially the root was 10, now the root is 20, root element is 20. Okay, so this is the benefit of using AVL trees. The root changes, okay, according to the requirement for balancing the tree. Root is changing. Okay, so we have another element here, we had 30. Okay, now we are suppose inserting 40. Suppose we want to insert 40. Okay, suppose we want to insert 40, so 40 will obviously again will be on this side, because since 40 is a greater element than 30. So but again you can see that you need to calculate that is this tree balanced or not. So again I think that this tree is actually balanced. The height of this is actually 1 minus 2, that is -1. Yeah, correct. Again this height is, you can see that this height is 0 minus 1, that is -1. Again fine. Okay, again the height of this side is actually 0. So you can see that this is balanced tree, so we don't need to perform anything on this. We can actually continue. Okay, now we are about to insert 50 here. Okay, so we are about to insert 50 here. What I'll do is I'll again say 20 first element, then 10, then next element is actually 30. Okay, then the next element is actually 40, then the next element is you are about to insert 50 here. Okay, so when you insert 50 here, now you'll see that this is an unbalanced tree. That means you can say that this is almost a right skew tree. It's moving towards the right side. So we need to fix this. Okay, so we'll simply say that we need to find the node which has problems, the node which has problems. So in our case, what node has problems, which node has problems? Okay, obviously this node, that is you must always start from the bottom. I would say that you can start from the bottom. So you say that this height is 0, this height is -1, okay, -1, and this height is -2. So this is the first node which has problems, and obviously the above node also has problems, but first we'll be encountering this. Okay, first whatever is the node, we'll be encountering this. Okay, I hope you get this. So here what do we need to do is actually, you would simply say that this is the case for what? This is the case for, again, right, fine. So you simply need to perform rotation here. So what you'll do is, again, I'll just say that rotation will be simply, you'll be again targeting from 20, and then this is the 10, and okay, I hope this is fine. Okay, and this is, now you'll say that 40 will become the middle element, since we are performing right. So 40 is the middle element, then 30 is here, and 50 is here. So you can see that now it's again balanced. Okay, it's again balanced. So if I again calculate the height, let's calculate the height. So you will see that 20 is actually fine here. So you'll say that the height of 40 is actually 0, and the height of 20 is actually, you'll say this is one node, and these are two nodes here. Okay, whatever is the longest from 20 side will be calculated. Okay, this is the longest, or you will say this is also the longest. 40, 50 is also longest. You can pick any. Okay, whatever is the longest, you need to pick that. So height is from 1 minus 2, that is again -1. So now things are in our range. Okay, so you can see that we didn't encounter 20, we simply changed position of 30, and it simply also made the node value of 20 fine. Okay, balanced. Okay, so you can see that this is now again a balanced tree. Okay, we are performing the balanced tree operations again and again. Now the last element is 25. So what to do with 25? Simply you will say that we now have 25. Very complicated. So you'll say that where must 25 come first of all? So this is again 10 on here, and then we have 40 here, and then we have 30 here, and what it will do is simply it will again make our things worse. Okay, so here you'll see that if I want to insert 25, it will be on left side of this side. Okay, I think this is following the rules of BST. First you need to check first it follows the rules of BST. Yeah, it's following the rules of BST, things are fine. But now you can see that if I take the height of this is 0, and this is 1, and this is actually 2 here and 1 here. Okay, so it's actually mine, yeah, it's actually 1, the height is 1. Okay, so you can see 2 is on the left side and 1 is on the right side. That means the height is 1. 2 minus 1, 1. Now you need to check for this one. So height here is 1 minus height here is, the maximum height is actually 1, 2, 3. That means 3 elements on the right side for 20. Okay, so you'll see that it's actually -2. So it's violating the rules again. Okay, violating the rules again. So now what do we need to do? We can simply see that if I talk about this, this is the case for what? This is the case for what? Right, and then left. This is the case for right, left. If I start from here, this is the case for right, left. Okay, the problem is with this node. Okay, so we'll be starting from here. 20, 40, 30. This is right L. So first of all, you need to convert RL to RR. Okay, so what you'll do is you will be starting from RL to RR. Okay, so RL to RR, since it's not resolved, so we'll be just making it to with red. Okay, so what I'll do is I'll just say that my root node is 20, okay, again 20, and then I'll say that my left side is 10, then my right side is, now you need to make sure that you are performing RR here, okay, right, you are performing RR here. So 30 will be actually switched with 40, okay, 30 will be switched with 40, and the direction of 30 will change, okay, direction of 30 will change. So what will simply happen is, you will say, so I told you that when the direction changes, okay, direction of 30 will be actually becoming the position of 40, okay, 30 will be actually here where 40 is right now, but also 40 will become right child of 30, okay. If I give you an example here, what we did here was to convert RL, we simply did was switched B and C positions, and now B is actually on the right side, okay. So you can see, if you assume it as, you assume it as 40, okay, you assume it as 40 in our case, don't worry about the other childs, just see here, and then we have 30 here, okay, this is our case, right? So what will happen to this is, actually 30 will be here now and 40 is here, then we'll see other childs also of 30 and 40, but yeah, this is the case for 30 and 40. So here you'll simply say that here you need to write 30, okay, then you have 40 here, okay, and whatever was the 40 child, you write it as it is, that's it, as it is, okay. Now what happens to 25? What happens to 25? So 25 is still the left child of this, okay, still the left child of this, okay, I hope this looks fine, still the left child of this, okay. So it's fine, but now you need to perform RR operation, okay, we converted RL to RR, okay, but we need to perform RR operation now, okay. So first conversion is made, whenever you have RL, you need to convert it into RR, then RR operation is performed. So here the final outcome will be, actually here you will simply see that RR will be again performed in this case, okay, that is this one, this is 2, this is 3, again RR is performed here. You can see we are actually now in RR. Initially it was RL, initially it was RL, now we are in RR, okay, now we are in RR. Always it will happen always with RL will be converted to RR, LR will be converted to LL, okay, fine. So here you'll simply say that here we will simply perform a rotation operation. 30 will now become the middle element of 20 and 40, okay. So you'll simply say that we have 30 here, fine. Now on the left side of 30 you will be having 20. Now on the right side of 30 you will be having 40. Now what about the other childs? Simply write it as it is if available. So if you have 50 here, you can simply write it as it is, okay, fine. Now for 30, now for 30, you know, we had a left child 25, but right now left child's position is taken by 20, okay. So what you'll do is simply assign that left child to whatever is on the left, okay, whatever is on the left. So you can see whatever is on the left of 30, that is 20. 20 will now have a child named as 25, but in which side? Obviously 25 is greater, so 25 will be on this side, okay, fine. And obviously the left child was 20, was always 10, okay. So you will work like this, okay. Suppose if 20 had a left child, so you will again switch 25 here, okay. So it works like that, but yeah, it's fine now, and you can see that it's working fine, okay. So this is actually an AVL tree, and this is actually decreased height, okay. So if you draw a simple BST tree out of it, okay, if you had to draw a simple BST tree, what would happen is 10, 20, and suppose we had 25 here, and then you had 30, then you had 40, then you had 50. So you can see that the height is BS or BST is very much as compared to AVL. So this is the problem which AVL solved, and I gave you a very great example. Now we will simply learn the next example, that is red black tree, okay. So this is also very important. Somebody wrote repeat please. So brother, you can do one thing, you can watch the video again. If you have any specific doubt, you can ask me that, okay, but I can't repeat because this video is very much lengthy, okay. So please watch the video again, and this will always be saved, so you can watch again and again, and you can refer the articles of Geeks for Geeks. If you still have doubts, you can message me on any of my live chat. And one more thing, if you want to contact me, you can message me on Instagram also, at the rate Harshal_3011 is my username, okay. So you can also ask your doubts there also. All right, fine. Okay, so now we'll be starting with red black tree. So since you have understood AVL tree, if you don't know AVL tree, again you need to watch this video, or you need to watch BST also. Like if you don't know BST and AVL trees, BST has been told before, but in this video we have covered AVL tree. Now if you don't know AVL trees better, you again watch this video. Okay, you learn things again and again, because these operations will be used in now red black tree. Okay, so red black tree is a bit more complicated here, because I think that red black tree solves a lot of problems. Okay, solves a lot of problems, and it's a bit, you would say, easier for others. But yeah, I found it very difficult to learn when I was a beginner. So we'll start. Okay, I'll try my best to make you understand this tree, because this is a very important tree and the most complicated one which you learn anytime. Okay, the most complicated tree you'll learn in your life. Okay, so definitely more complicated trees are introduced, but yeah, for DSA purposes we learn these kind of trees, AVL trees or red black trees. And now we'll be drawing that. Okay, we'll be drawing that. So first of all, you need to know that there are actually some rules. Okay, just learn these rules and we'll be using these rules. That's why first of all I'm writing the rules for creating a red black tree, for having a red black tree. So I'll just say, okay, too bold. Rules for red. So red black tree simply means we decide the color of our nodes. Okay, this is the new thing. And rules for red black is simply we are deciding the color of our nodes. That means one node can have red or black color for some conditions. Okay, so this simply means either the node color is red, either the node color is black. That's it. Okay, so we'll be writing rules for that, because you can't write as it is. Okay, you can't give random red and black nodes, that will be problematic. Okay, so first we'll start. So I would say that first of all, whatever is your root will always be black. Root is always black. A red black tree can be identified simply by these rules. Okay, these are some identification rules. Okay, not for creation, these are some identification rules. Okay, so you'll say root always black. Okay, root must always black. For creation we'll be writing some other insertion rules. Okay, this is just for identification for red black tree. If you want to identify if the tree is red black or not, you can use these rules. So root of the tree must always be black color. Okay, then the second can be actually left. That means the leaf childs will be black. Okay, so what is the second rule? It simply says that the leaf child will always be black. Okay, leaf child, that means the null after the leaves. Okay, the leaf is supposed to and it does not have any child. Okay, that means the null childs are present, those null childs will be of black color. Okay, you can assume that. Okay, the leaf can be of red or black color, it doesn't matter, but the childs of leaf, that means nulls, are always black. Okay, I'm talking about nulls. Okay, so you'll simply say that leaf childs always black. Fine. Then we have some third case. This is also another case for identifying. So if we have a red child, it its parent can never be red. Okay, if suppose if I talk about this case, suppose this is a red colored node, its child can't be of red color. Okay, its child can't be of red color, it must be actually, like, suppose if the parent is black. Okay, if the parent is black, then its child can be either red or either black. Okay, you can assume it like this. So this is actually a valid case, or this is also some valid case. Okay, this is also some valid case, or another case can be actually this is also a valid case. But red can't be together. Okay, red, okay, sorry, yeah, red can't be together. So you can see that what's the valid case. This is actually the valid case, this is the valid case, and this is the valid case, both for left and right childs. But parent and child can't be both red. Okay, you need to know this. So this is the third rule. Okay, so I'll just write it here. uh Red parent and child not allowed. Fine, this is the rule. So if you see red parent child combination, that is not a red black tree. Okay, fine, this is the third rule. Now we have the fourth rule. All leaf childs have same black depth. That means if I have two black childs, okay, that means if I have two black nodes, suppose always the root node will be the black node. This is the root node. Okay, this is the root node. And if I have one black node and suppose we have a red node, I'm just assuming an example, I'm just giving an example. Okay, this is an example, and again I have some black node, and so on. Okay, and so on. So don't worry about the leaf can be of any color, but leaf child must always be black. Okay, if I talk about its null childs, they'll be always black. Okay, but this leaf, that is this black, can actually be of any color. Okay, red or black. Okay, similarly if I have two black childs here. Okay, so if I have one black child here, suppose this is the tree, suppose this is a tree, you just assume it. This is not a valid tree, this is not a valid tree, as you can see that on the left side we have two black nodes, 1 and 2. Okay, on the left side we have two black nodes, that is 1 and 2, but on the right side we have only one black node. That means this is not valid, because on both sides we must have equal things. That means on any branch, okay, I'm talking about on any branch, if you talk to the end, if it had all other branches also, you need to compare for each. Okay, every branch will have same black number of nodes. If this branch has two black number of nodes, this branch will also have two black number of nodes. This another branch will also have two black number of nodes. This another branch will also have two black number of nodes. It's like that. Okay, so you'll see that it simply means that now the problem with this is it does not have same black number of nodes. Okay, so the correct one is actually something like, if you have two black nodes here, suppose if you have two black nodes here for some case, then you must have two black nodes here also. Okay, it's like that. Okay, obviously you will be having some red nodes also, but yeah, there must be equal number of black nodes on any side of the tree. Okay, fine. So now similarly, this is the fourth rule, that simply says that black nodes on each side must be same. Black nodes on any, you'll say on any path from root to node. Okay, so from root to leaf, root to leaf must be same. Okay, so I hope you got this rule. Now we can continue with the drawing part. Okay, so this is important. So there are actually some rules assigned for AVL trees. So for actually performing insertion on AVL trees, right now we have seen the rules for judging an AVL tree. Okay, sorry, judging a red black tree. I'm sorry, judging a red black tree. This, if the tree is red black, it must follow these rules. Follow these rules. Now we'll be writing rules for insertion, how to insert an element in a red black tree. Okay, so for that you can say that insertion rules. Okay, so there are actually some insertion rules which you must follow in any red black tree. These are very important. So first rule is actually, if tree is empty, create a new node with a black color. Okay, if tree is empty, create a new node with black color. That's it. First node will be black color. Okay, root node will be black color. So it simply means that if tree empty, then first element, that is root, will become black. First element black. Okay, whatever you are inserting will be black. Okay, now second rule for insertion is, if tree is not empty, create node as red. Okay, so if it is empty, it will be first element as black. Okay, if it's not empty, create node with red color. Okay, create node with red color. Obviously you might be having some other element before, so create red node. Okay. Okay, so now I think it's fine. So this is the second case. Now what is the third thing which you need to make sure is, third thing is actually, if the parent is black, then exit. Okay, so whenever we are performing insertion, okay, then we simply insert the element. Okay, we assign that color as red. Suppose this is the case, suppose you have one element always present. Okay, suppose you are inserting some other element, suppose you are inserting the second element, you need to see that if this element, the new element's parent, is black or not. So you can see its parent is black, and what I told you, that any red can have black parent, but any red can't have red parent. Okay, so this is a valid case, this is a valid case, so you don't need to do anything, you can simply exit. You need to perform just simple insertion. Suppose it was before 10, now I inserted 18 here. Simply perform this insertion and then exit. You don't need to perform any recoloring or rotation. Okay, so this insertion rules are actually for when you need to perform recoloring and rotation. So this is the third case. Now we will be looking into the fourth case. So for the fourth problem is, if the parent of new node is red, then we need to see, if the parent of new node is red, then we need to see that, check the color of parent sibling, that means my uncle. Okay, parent sibling simply means my uncle. So what I'll do is, first of all, I'll just write the rule and then we'll see a practical logic for that. Okay, so here what we can do is, if parents color is red, then see uncle's color. Uncle's color simply means parents real brother or sister. Okay, parents real brother or sister, not other siblings from other branches, only the parents real brother or sister. Okay, that means if I talk about 18, 18 is child, 10 is parent. Okay, and suppose the parent of this is also something like, suppose this also has some parent. Okay, suppose this also has some parent, which is suppose 5. Okay, and suppose on the left side we had 3. Okay, so you can see, if 18 is child, 10 is actually the parent, and 3 is actually uncle of 18. Okay, I hope you got this. So we need to see the uncle's color. So we'll see the example. This is just the representation of uncle, parent, child. Okay, uncle, parent, child. So it can be auntie also. So here, see the uncle's color. Okay, so now if uncle's color is black or null, uncle's color is black or null. Okay, so I'll just write uncle with black. Okay, uncle is black. Okay, uncle is from Africa. So sorry, I'm just kidding. Okay, so uncle color is black or null, then rotate and recolor. Okay, rotate and recolor. So it will simply mean that we need to perform rotation operation as well as recoloring. Okay, rotate and recolor. Right? And similarly, if uncle's color is red, I don't know what humans look like red, but yeah, red. Okay, uncle's color is red. Okay, actually this is also valid for black or null. Okay, if uncle does not exist. Okay, uncle does not exist, then it will also be null. Okay, it will be null actually. So you'll simply say that it's actually null. Okay, so either the uncle's color can be black or uncle is already null, then you need to perform the both of the operation, rotate and recolor. Okay, you don't need to perform any rechecking on the above child. Okay, this is only for rotation and recolor, no recursion. Okay, no recursion or no recheck. Okay, only one time operation is performed in this case. But if this is the case, what you need to do is, first of all, you need to perform recoloring. Okay, first of all, you need to perform recolor. Then you need to say that if parents of parent node is not the root. Okay, then you need to recolor and recheck. That means my parent, that means first of all I perform the recoloring. That simply means that if my uncle is of red color, I'll change the color of my uncle and also my parent. Okay, my parent will become red. Similarly, same things will happen. Suppose for example, it simply means that when my parent's color is red. Okay, so what can be the case? The case can be, suppose you have this parent. Okay, you have this parent. Okay, this is the root. Suppose this is the root, and this is, suppose, uncle. Okay, suppose this is uncle. So uncle will be of, suppose we have red uncle and we have red parent. Okay, we have red parent, red uncle, and then suppose we also have, obviously you are inserting a new child, so it will be red child. Okay, so red child had this red parent and red uncle. Okay, so this is the fourth is the case. Okay, fourth case, we are on fourth case. That means child's parent is actually red. In fourth case, this is the first case, that is A, and this is the second case, that is B. So first case was actually uncle is black. No, uncle is not black. Uncle is actually red. Okay, uncle is actually red. So we need to see that first of all we need to recolor it. Okay, we need to recolor it. Okay, we need to recolor it. Recolor both. We have recolored them. Then we need to see that my parent has color. No, we need to see that my parent is the root node or not. Yeah, this is the root node. This is the root node. Then don't do anything. Don't do anything. Okay, don't do anything. Okay, I'll say that I won't be writing it here because I think screen is hiding. So what I'll do is I'll just write it like this. Parents parent root, which equals don't do anything. That means insertion is fine. Insertion is fine. Okay, but if parent wasn't the root node, then what you will do? If parent wasn't the root, sorry, if parent wasn't the root node, what you will do? I'll just give you another example. Suppose my parent, suppose we'll say, now we are in this case, we have performed recoloring. Okay, we have performed recoloring, and you can see that this is the current case. Okay, but in the same current case, if the top one is still not the root node, it might be having some other parent, okay, some other parent, then we need to check its color. This simply means that if parents, this is our parent, right? This is our parent. If it's having a parent, that is this parent, and this color, okay, and this is not the root. Okay, this is not the root. You might be having more parents above that. Okay, more parents. This is not the root. Suppose the root is somewhere else. Suppose the root is somewhere else. Okay, but right now we are talking about this Dadaji. Okay, this Dadaji. So this is the child. This is the child. This is the parent. Okay, this is the parent. This is the child, and this is Dadaji. Okay, that means grandparent. Okay, grandparent. So it simply means that the grandparent is not the root node in this case. So what we'll do is we'll recheck for this case. Okay, we'll recheck for this case. Recheck simply means, I'll say parents. First of all, I'll just write it. Okay, sorry. Parents, parent, that is grandparent, is not root. Okay, it's not root in this case. So we'll simply recheck. Recheck simply means and also we need to perform recolor also. Okay, we need to perform recolor also. Okay, It simply means that we need to recheck for the parent. Same case, same fourth case. Okay, if its color is black, then we'll just recolor, else we will recolor and rotate. Okay, so same fourth case will be repeated for this now. Okay, since it's not the root, fourth case will be again repeated. Fourth case is what? This one. Fourth case is the top one. Okay, which we read. So it simply changes the parent. Now the parent is not this one, parent is this one, and we'll check its color. If its color is red, then we'll simply perform the B case. If its parent is recheck simply means that here what I'll do is, yeah, now it's fine. So here you can see above what we do is you can simply say if the parent is black, we are simply exiting. Okay, so this simply means that my parent is actually black. My parent is actually black. So I'll decide that either we have to leave or connect with this. Okay, leave or perform the operation 3 and 4 with this. Okay, so this is somewhat rules which we will be looking into the red black tree. Okay, right now I've just explained a bit of rules for insertion, but we'll be performing it live on by writing some rules for that, by writing step-by-step approach for that. We have just written some random rules which are required for it. Definitely I think I might have missed some rules, definitely, but yeah, we'll be drawing a diagram for that so that you get a better idea for this. Okay, so in this video we have covered things, but I think this is too long, so we'll be covering the next part in the next video. That means the step-by-step diagram for creating any red black tree we'll be looking into the next video, how to perform insertion operation, and in the next video we'll be also looking into binary heap. Okay, and then the coding part remains, so we'll be covering that. Okay, so I hope you understood this video. In the next videos we'll be covering more out of trees and the remaining parts of DS data structures, that is graphs is also remaining and linked list is also remaining, and some kind of data structures are remaining, so we'll be covering that. Okay, so I hope you understood this video. We have covered AVL trees, explanation of that, how we draw diagrams with that, how we perform insertion with that. In the next part we covered the red black tree. In this we just understood some rules and also the insertion rules for that. Okay, so we haven't covered the step-by-step approach for creating a red black tree, but we'll look that into next video. Okay, so I hope you understood this video. If you have any doubts you can ask me on the live chat, and I think okay. Okay, so I think it's fine and I can end this video. In the next video we'll be covering the part 2 of the same. Okay, so that's it for today. I will see you in the next one. Till then, see, have a good day. Bye bye.